In this video, we're going to go over section 10.5 from our textbook, which is on solving trig equations. So the first thing we're going to look at is solving trig equations using linear methods, and we'll do so using this example here. We want to solve this equation over this interval here and for all possible solutions outside of this interval. So we can see that this equation involves the first power of sine theta, so it must be linear in sine theta. So we'll write that here. This is going to be a linear equation. So the first thing that we'll do is isolate sine theta. So first we'll subtract 2 on both sides of this equation. We have 4 sine theta is then equal to -2. And then dividing by 4 on both sides, we get sine theta is going to be equal to -1/2 since we have -2/4. So this tells us that theta must then be either equal to 7 pi over 6 and 11 pi over 6. Because at these angles, we can see that sine is going to be -1/2 and -1/2 here. So the solution set is going to be 7 pi over 6 and 11 pi over 6. And this is for our angles theta in between 0 and 2 pi. Now we're also asked to solve this equation for all solutions. So in this case, what this means here is our solution set is going to be slightly different. We want to include all solutions outside of this interval here. So for example, we're saying that 7 pi over 6 is the solution here because in this case, sine of 7 pi over 6 is equal to -1/2. But if we were to add one full rotation, this answer would also be a solution. This angle would also give us -1/2 here. If we were to do the same thing and add another rotation, we get the same thing. And similarly for this angle here, 11 pi over 6, if we were to add one full rotation here, we would also get sine of that angle is equal to -1/2. So we write our solution set as the following here. We'll say it's going to be 7 pi over 6 plus 2 pi, that's one full rotation, n. And n is going to be any integer, so this is going to be any multiple of 2 pi n, or any multiple of 2 pi. So if n was equal to 1, then we would do one full rotation. If n was equal to 2, then we would do 2 full rotations, and so on and so forth. And similarly for 11 pi over 6 here, we're going to add a multiple of 2 pi to that, and then we say n is any integer. So that would be our solution set for all solutions outside of this interval, looking at multiples of 2 pi. All right, let's look at another example. We want to solve this equation over this interval and also for all solutions. So we're going to do the same thing. We're going to solve for our trig function. So first we'll subtract 2 on both sides. We'll get 3 tangent x is going to be equal to -3. And then dividing by 3 on both sides, tangent x is going to be equal to -1. So looking at our unit circle, that's going to be, because tangent is going to be sine over cosine, so when tangent x is going to be equal to -1, this is going to be when sine and cosine are going to be opposite values, or opposite in sign. So for example here, 3 pi over 4, cosine is -√2/2 and sine is √2/2, so sine over cosine would give us -1. And similarly for 7 pi over 4 here for the same reasoning. So x is going to be equal to 3 pi over 4 and 7 pi over 4. So our solution set will be exactly that over the interval 0 to 2 pi. Now for all solutions, let's do that up here. By the same reasoning, we want to capture all rotations outside of the interval 0 to 2 pi. So this will be 3 pi over 4 plus a multiple of 2 pi, which we'll represent with 2 pi n, and 7 pi over 4 plus this multiple of 2 pi n. And then n is any integer. Because remember, if 3 pi over 4 is going to be a solution, so would one full rotation, and another, depending on the value for n. And similarly for 7 pi over 4, this is a solution. One full rotation would also be a solution, and so on. Alright, so let's look at another method here. This method is solving by factoring. So we'll illustrate this with an example here. We want to find the exact solutions for this equation. We'll just write it out again here. So we have sine theta cosine theta minus sine theta is going to be equal to 0. As you can see, both of these terms here have a sine theta in them, so we can pull that guy out. And so we get this here. Now this becomes a problem we're pretty familiar with. If sine theta times cosine theta minus 1 is equal to 0, then either sine theta is equal to 0, or cosine theta minus 1 is equal to 0, or both. So we have sine theta is equal to 0, or cosine theta minus 1 is equal to 0. Now when sine theta is equal to 0, looking at our unit circle here, we know this occurs at pi and 2 pi. And then for this guy here, we'll just solve for cosine theta. So we'll add 1 on both sides. So we'll get cosine theta is equal to 1. And then looking at our unit circle, we know that this happens at 2 pi. Alright, so then our solution set we can write in the following way. We know for this to be true, theta must be equal to pi or 2 pi, and for this to be true, theta must be equal to 2 pi. So our solution set is going to be pi n, where n is any integer. Right? Because if n were to be equal to 1, then our solution would just be pi. If n were to be equal to 2, it'd be 2 pi, and so on and so forth, depending on the number of rotations that we do. So this would be our solution set for this example. Alright, so the next thing we're going to look at is solving these trig equations using the quadratic formula. So if you remember, this is the quadratic formula here for an expression that's in standard quadratic form given by this here. So we'll illustrate this method with this example here. We want to solve this equation over this interval, and this is going to be in standard quadratic form. If we think of tangent theta as x in this case. So in this case, a then is equal to 1, b is going to be equal to 4, and c is going to be equal to 2. And the unknown that we're trying to find is going to be tangent theta. So we'll say this is equal to question mark. So we're going to use the quadratic formula here. So we have tangent theta is going to be equal to this here. And so we'll substitute our values for a, b, and c into this equation. So we have 4 plus or minus the square root of 4 squared minus 4 times a, which is 1, and c, which is 2. That's under the square root, and this whole thing is over 2 times our value of a, which is 1. So this gives us, and sorry, the formula should actually be opposite b there. So this guy should be negative 4. Alright, so we have minus 4 plus or minus. Under the square root, this will be 8, and this is still all over 2. Now remember, we can rewrite the square root of 8 as the following here using our prime factorization. So we're breaking this up into these two radicals. The square root of 4 we know is just going to be 2, so this will just be 2 times root 2. So we can rewrite this here as minus 4 plus or minus 2 times square root of 2, and again this is still all over 2. Since 2 is dividing both of these terms, we will get minus 2 plus or minus the square root of 2. Alright, so this tells us that tangent theta is going to be equal to minus 2 plus the square root of 2, which is going to be approximately equal to minus 0.5858, so we're just rounding this guy. And we also have that tangent theta is going to be equal to minus 2 minus the square root of 2, which is approximately equal to minus 3.4142. Alright, so we have these two solutions because of our quadratic formula, which includes this plus or minus here. Now, solving for theta by using arctangent, we'll do this here in our calculator. Now this gives us this here. And then for our other equation here, doing the same thing, this gives us this here. So this is what we have for our angle theta, but this is where it can get a little tricky. So when finding these solutions here, we want the smallest positive angle. So when we have these negative angles like this here, what we'll do is we'll add one full period of our tangent function. And that would be pi. So we'll have negative 0.5299 plus pi, which we're approximating with 3.14. This will give us 2.61. And similarly for this other guy, we'll take negative 1.285 and we'll add 3.14 and we'll get 1.86. Now these will be two solutions in our solution set. However, we wanted to solve this guy over this interval here. And so what we'll do to make sure that we include all solutions within this interval is we're going to add another period to both of these guys. Since tangent's period is pi, we'll typically get two solutions for each value of our tangent theta. So we'll call this one theta 1 and this one theta 2. Our potential theta 3 then would be equal to this guy plus 1 period. So 2.61 plus pi, which is approximately, or this is exactly equal to 5.75. And similarly, adding pi to this guy here, we will get exactly 5. And notice that these two solutions are within this interval here. So these will also be part of our solution set. Now, if you were to add any more periods to these guys, this would be outside of our interval, so those would not count as solutions. But in this case, since all four of these are within the interval the question asks us to look at, we have these four solutions in our solution set. All right, and this is for this interval. And something to note here, if we were asked for all solutions, our solution set would be multiples. We would take this guy and then we would add multiples of pi, and then this guy and add multiples of pi, where we know n is any integer. All right, so we're going to look at a couple more examples of this. So in this case, we want to solve this guy over this interval. Now, this is going to be a quadratic equation here, but this is where our trig identities come in hand. Remember, secant squared x is going to be equal to 1 plus tangent squared x. So we can rewrite this guy in those terms, and our entire equation will be just in terms of our tangent function. So we have 1 plus tangent squared x. So just plugging in our identity for this guy, plus 2 tangent squared x is going to be equal to 1. Now we have 1 tangent squared x and we have 2 tangent squared x's, so we can add these guys together. We'll combine like terms. This will give us 3 tangent squared x. Alright, so now we'll solve for our tangent function. First thing we'll do is we'll subtract 1 on both sides here. This gives us 3 tangent squared x is equal to 0. Dividing by 3 on both sides, we'll get tangent squared alone, and we'll still have 0 on the right-hand side of our equation. And similarly, square rooting both sides of these guys gives us our tangent function, and we still have 0 on the right-hand side of our equation. So we want to know when tangent of x is equal to 0, and this is only going to happen at 0 and pi. Remember, tangent is sine over cosine, so this is only going to happen when sine is equal to 0. So our solution set then is just going to be 0 and pi over this interval here between 0 and 2 pi. And then for all solutions, we would have 0 plus a multiple of pi, and then pi plus some multiple of pi. Alright, let's look at this last example here. We have this quadratic equation here, and we want to solve it over this interval. Now, in this case, we don't have to use our quadratic formula because this is actually factorable. If we kind of think of sine x in terms of one variable, we can factor this guy as sine x plus 3 times sine x minus 2. If we were to FOIL this, we would get our original equation here. So this tells us, for this to be true, either this needs to be equal to 0, or this needs to be equal to 0, or both. So we have sine x plus 3 is equal to 0, or sine x minus 2 is equal to 0. This tells us sine x is going to be equal to minus 3, or sine x is going to be equal to positive 2. However, we know that our sine function is only going to be between negative 1 and 1. So this tells us there is no solution. So our solution set would just be the empty set, which looks like this here. Alright, so that's the last example for this video, but here is a list of the steps for solving these trig equations analytically. First, you want to make sure you know what type of equation you're working with. That'll be linear or quadratic, so you can determine the solution method that you want to use. Then you'll solve for the trig function if only one trig function is present. Now, if the equation has more than one trig function, then we'll rearrange the equation so that one side is equal to 0, then try to factor and set each factor to 0 so we can solve it. Now, if the equation is not going to be factorable, but it is in our quadratic form, then we can use our quadratic formula. And if we don't need to use our quadratic formula, then we can use identities to change the form of the equation and try to simplify it so that we are able to factor and solve. Alright, so these steps will be helpful for solving these equations, and that'll be it for this video.